Hi all. The next few lectures are devoted to the study of reinforcement learning or RL, which is essentially a form of online learning problem with state. Okay, so with the notion of state of a system. So what is broadly reinforcement learning? There are two definitions here that I'd like to present. The first definition given by Kaelbling, Littman and Moore earlier on in 1996 is that RL is a class of learning problems which are faced by an agent that wants to learn how to behave in an ideal way through basically trial and error type of interactions with a dynamic environment. So, we will see how to express these concepts formally, but the key takeaway from here is that the problem is to learn how to behave when you are interacting with an environment that itself can evolve or is dynamic. A second definition, which is perhaps closer to what we will study in this lecture, is that reinforcement learning presents a framework to think about decision making when the current decision of the learner or the learning agent can affect future opportunities or possibilities. Okay, so in some sense the connection between these two definitions is that the learner has to learn interactively by taking decisions or actions within an unknown environment, which in turn has the ability to react or evolve in response to the successive decisions or actions of the learning agent. So, this is at a high level what the problem or class of problems called reinforcement learning problems are all about. And this framework of reinforcement learning has been used to great effect in domains which are fairly complicated to admit solutions by other approaches. So, some of the most popular example domains where RL has proven to be very useful are the control of physical systems, for example, objects like robots or manipulators or robotic arms, or even for instance autonomous cars. It has also been used to great effect in trying to solve games defined by a fixed set of rules. For instance, Tetris is a game where blocks or bricks fall down and one has to learn to optimally place them in order to accumulate as high a score as possible. Chess is another classic game in which one must train an agent to learn to play the game well and to win as many games as possible. Go is a similar board game to chess. StarCraft is a multiplayer online game which also has seen successes due to the application of reinforcement learning methods to train autonomous agents that can play this game well. In other settings, RL has been used to design resource allocation algorithms or learn resource allocation strategies, let's say in communication networks, in the control of power systems, and more classically, a field of standard control theory called adaptive control, which is somewhat related in spirit to reinforcement learning, has also been studying approaches to try to learn how to automatically control systems, and this is often applied to learn strategies for flight guidance, flight or aerial tracking and stabilization and so on. So, RL is a fairly general purpose framework that allows one to frame problems of learning to control or behave optimally within the context of an unknown dynamical system. So, let us go on to the mathematical modeling of RL problems and the way that they are formally expressed. So, one of the most popular approaches which has stood the test of time to express reinforcement learning problems is what is called the Markov decision process or the MDP model. It is also often called the Markov reward process model in some contexts. But we will prefer the term MDP. So, what is an MDP, a Markov decision process? The mathematical definition of a Markov decision process for our purposes during the context of these lectures is that an MDP is a tuple. More precisely, it is a 6 tuple that we write as S, A, T, R, H and rho. So, it is a 6 tuple where S stands for the state space of the system, of the unknown system or the environment. So, this is just a set of states, possible states. A is referred to as the action space or the decision space. So, action or decision space. It is the space of all decisions that can be made from the point of view of the agent or the learning agent. T is the state action transition probability function. Or also called sometimes as the dynamics function of the environment. R is called the state action reward function. Let us just call it the reward function in general. And it can be a function of either the state or the state action. H is something that we will call the time horizon of the MDP. So, this is a positive integer, and rho is a probability distribution on states that is associated with the initial state. So, it is the initial state distribution. On the set of states S in our notation. So, by the way, before we move on, we note that we will only, for purposes of clarity, consider the class of finite horizon MDPs, which is why we define explicitly a time horizon as part of the definition of an MDP. There are extensions of the theory of Markov decision processes and optimal control and reinforcement learning to what are called infinite horizon Markov decision process problems, but we will not study them due to a lack of time. We will also conveniently assume that the state and action spaces are always finite along with a finite time horizon. So, this is the realm of finite state, finite action and finite time horizon MDPs. So, for more general theory, you can consult this excellent reference by Dimitri Butsekas, which is the textbook on dynamic programming and optimal control. So, let us delve a little deeper into the definitions of the T and the R objects or parts of the MDP, which are probably the most important parts of Markov decision processes for the point from the point of view of reinforcement learning. So, for any pair of states S and S prime and for any action A, we denote by T S A S prime the probability of transitioning from state S to state S prime when an action A is taken at state S. Okay, so, this is the probability of transitioning to state S prime when the action A is played or taken at state S. Okay, so, by this definition, we naturally have that if you sum T of S comma A comma S prime across all S prime in S, then this must be equal to 1. So, if you take an action at some state, then with some probability you will transition to another given state. Okay, and so that is the definition of the T function. So, T accepts 3 arguments, 2 of which are states S and S prime, and the last argument is an action. and it spits out a probability value. Okay, so think of so in pictures you can think that the current state of the environment is S, and an action A was taken, and in response to having taken this action A or decision A at state S, you could transition to one of several next states. So let us say S1, S2 and S3 with the respective probabilities T SA S1, T SA S2 or S3 with probability T A S3 SA S3. Okay, so this is a probabilistic model for state transitions, but with the additional influence of an action A that one can play at a given state. R, the reward function R, which we will define for the scope of these lectures as dependent on S and A, just stands for the reward. So it's a measure of utility or reward obtained when action A is played at state S. Is played or taken at state S. Okay, so one important note here is that this is not the only way in which rewards are defined. Rewards, for instance, can also depend. So let me just make a couple of notes. So reward can depend in general on the current state, the current action, and also the next state, but we only assume, just for simplicity, we assume the dependence only on S and A. The second note here or remark is that R of SA, so suppose you played an action A at state S, the reward that you could get could actually be a random variable. RSA can be a randomized function. Okay, so this is the same as saying that the reward from playing action A at state S could be sampled independently from a distribution associated with the state S and the action A each time action A is played at state S. Okay, so we do allow this possibility. So for example, if you played a certain action A at state S, you could probably have a reward which is distributed as a Bernoulli random variable with some parameter mu depending on S and A. Okay. Right. So so T and R are the state transition and reward functions for an MDP. The state and action spaces are just sets of states and actions. The time horizon and the initial state distribution is something that will become clear shortly when after we define what is a policy. So what is a policy? A policy for an MDP represented by this tuple S, A, T, R, H and rho is just a map or a function. Let us call it pi, that takes as input any state and any value of time between 1 and the time horizon. So that is the integers 1, 2 up to h, and spits out a probability distribution over actions. Okay, so delta A as before is a notation for the set of all probability distributions over the action set A. Okay, so what a policy does can be interpreted as follows. So, here is an interpretation of this definition. At any time denoted by small h, so you should think of time as decision rounds within the time horizon. Okay, so bracket h is the notation for 1, 2, 3 up to h. If the MDP, if the state of the system or the environment is in state S, then the policy pi is assumed to play the action or take the action, takes the action A, takes an action A, a candidate action A, with probability depending on the state S and the time horizon given by pi. So, with probability pi, so what pi does is it applies, so the policy applies the pi function to the current state and to the current time index. So, pi of SH is a distribution over actions, and the probability that this distribution assigns to this particular action A is the probability with which the policy is assumed to be playing the action A at state S on around H. Okay, so this is true for any arbitrary action anyway. So, a policy roughly specifies how or which action to play as a function of the current state of the MDP. So, it is a rule to look at the current state of the MDP and potentially also the current timestamp small h, and then play an action which could be a randomized action as given by the distribution pi sh. Right. So, the moment we have a policy and over an MDP, we can think of a policy interacting sequentially with a Markov decision process. Okay, so there are two entities, there is an MDP and then there is a policy defined over the MDP, and you can think of a policy sequentially interacting with the MDP for capital H interactions called an episode as follows. Okay, so this is the protocol by which, so we are going to write down the protocol by which a policy interacts with an MDP in a sequential order. So, let us say the timestamp is initialized to 1, the smallest possible value of time, and the first state of the MDP is assumed to be drawn from the initial state distribution rho. Okay. And the following loop executes h times. So, while small h remains at most h, the policy makes a move in the sense that it looks at the current state and plays an action. So, this is potentially a randomized action AH drawn according to the probability distribution which takes as input the current state and the current time index, passes it through the policy function pi, and you can draw an action from this probability distribution over actions. Okay, so we can express this as the policy takes an action or policy plays an action followed by the play of an action AH. The MDP transitions from state SH to SH plus 1. So, it generates a new state drawn from the transition function that takes as input the current state, the action that was just played, and a dot to signify a distribution over the next states. Okay, so, SH plus 1 is precisely drawn from the distribution over states specified by T of SH comma AH. leaving the last variable free. So we can write this succinctly as the MDP. So the MDP transitions to the next state along with this transition. A reward is also generated by the MDP. So RH is drawn in general from the reward generating distribution. So it is a randomized sample of the reward resulting from having played the action AH at state SH. Okay, so the MDP generates reward which is received or observed by the learner. That's what we will assume in the later sections of these lectures. And then the round index increments. H is replaced by H plus 1. So this is the interaction loop that one can imagine between a policy and an MDP over which it is defined. Okay, so let's record this interaction protocol by the symbol star. So just to make things a little more intuitive and pictorial, here's a natural Markov structure or a dependency structure that expresses this sequential interaction between the policy and the MDP transition function as written above. So so what are the random variables in this that arise as this loop runs? Well, they are precisely the following. The first random variable that is generated is the initial state S1, right? Based on S1, the action A1 is taken. This is the policy part. Based on S1 and A1, the next state S2 is generated by the MDP, and along with this, based on S1 and A1, there is also a reward R1 that is generated. Okay, the process now repeats. Based on S2, the policy plays an action A2. Based on S2 and A2, the MDP's transition function generates the next state, which is S3, and also you can think of a reward R2 being generated at this point in time, and the process repeats. So arrows show dependencies. So any inward arrows pointing to a variable, let's say R3, mean that R3 is essentially a function of the of its parents, which send R3 incoming arrows. Okay, so this is the time evolution until the time horizon of capital H is encountered, and it's good to mark out what the dependencies precisely are. So S2 is generated from S1 and A1. This dependency of S2 on S1 and A1 is through the transition probability function T. The dependence of R1 on S1 and A1 is specified by the reward function R or the reward distribution R, and the dependency of A1 on S1 is through the policy pi. The policy pi is what describes or prescribes how the action A1 arises, purely depending on the current state S1. So the same dependency structure carries forward over time. Okay. So it's very useful to remember this kind of dependency structure because it encodes a natural Markov property. So for instance, we can write that under this, so Once we have this while loop, the probability distribution of the stochastic process involving all these random variables S1, A1, R1, S2, A2, R2, S3, R3, A3, S4 and so on is completely determined. Okay, so and we have a natural Markov structure here in the sense that the probability distribution of everything in the future starting from S4, so let us say S4, A4, R4 followed by S5, A5 and so on, given the value of the past up to state S3, let us say. So, S3 is the most recent state, going backwards in time R2, A2, S2, R1, A1 and so on is naturally seen to depend only on the most recent state S3. Okay, because so it does not matter how you got to state S3, everything in the future after S3 is independent of how you got to S3 given the state S3. Okay, so we can so a different way of expressing this property is that the future trajectory of this stochastic process is independent of the past trajectory given the present state. Okay. So, this is a natural Markov property that is very useful in analyzing Markov decision processes and policies interacting with them. We will see a use of this Markov property in a result that we will present at the end of this lecture. Okay. So, what are we interested in? What is the classical optimal control problem or the stochastic control problem? Well, for a Markov decision process and a policy interacting with it, the total reward from an episode, from an entire episode as given by this star, the box labeled star here, is just the total accumulated sum of the reward random variables RH. Okay, so note that RH was just defined to be equal to or more generally distributed according to R SH AH at time instant small h within the total time horizon capital H. Okay, so the total reward from an episode is denoted by the random variable that is obtained by summing the rewards from every step of this interaction between the policy and the MDP for a total of capital H rounds or decision rounds. Now, what is now, having defined the total reward from an episode when a policy interacts with an MDP, one can now try to define what we mean are good policies or optimal policies. So, an optimal policy for the Markov decision process SAT RH rho is one that solves the following optimization problem. So, any policy that solves for the maximum expected reward, okay, over all possible policies interacting with the same MDP, okay. So, here pi is any policy for the MDP and E pi is notation for the expectation over the trajectory of the entire trajectory during the episode. So, over the trajectory or the stochastic process comprising the initial state S1 A1 R1 S2 A2 R2 all the way up to SH AH RH, okay, generated by the interaction of pi with the MDP as given by the box labeled star. So, the interaction protocol star. Okay. So this is what is called an optimal policy. So finding an optimal policy is simply finding a way to play an action at every state and also potentially every instant of time that maximizes the total return within an episode. So it's important to note several special cases of the MDP model. In fact, the common stochastic multi-arm bandit problem. Stochastic multi-arm bandits can simply be viewed as Markov decision processes which are essentially stateless in the sense that there is only one state. There is no non-trivial state transitions occurring between two states, and moreover the time horizon h being exactly 1. Okay, so if the time horizon h is exactly 1, then it does not matter what the state is. Uh, the uh, the only thing here that is non-trivial is that the reward function RSA, which is equivalent to just a reward function R depending on the action that was played, just represents the reward distribution that you get for playing an action A. So there is no real dependence or influence of any state of the MDP because there is only one state at all times. So the total reward from an episode is exactly the reward that you get by playing every single action, okay, or the action of choice for the policy. A policy essentially reduces to a distribution over actions without regard to any state. Extensions of the stochastic multi-arm bandit model uh, for general state spaces but with time horizon h equal to 1 are often called contextual bandits in the literature on multi-arm bandits, in the sense that the state that arises at the single time step of the episode based on which the policy can play an action can be regarded as a context. Okay. So, it can be regarded as some context that helps you decide which action to play. Maybe this is relevant in applications involving let us say online recommendation systems on the internet where the context is set by the attributes of users of a user that visits the website, and an action A prescribed to a certain user may have a different effect than an action A prescribed to uh, a different user. Okay. So both these users can be treated as two different states depending on which user is active at any point in time. So we won't say more than this about contextual bandits. So let's move on to analyzing the structure of optimal policies. It turns out that for Markov decision processes, optimal policies have a very nice structure purely by virtue of the Markov property that arises out of the interaction between policies and MDPs. And one way of seeing this is what is called finite horizon dynamic programming, which we will formally express soon. So just to recap, an optimal policy pi star is any policy for a Markov decision process with a horizon h that solves the following optimization problem. It maximizes over all policies pi. So I should say here that pi is any policy for the MDP, for the finite horizon MDP. So it optimizes the total reward and expectation by basically choosing actions in some sense wisely depending on the current state and the current time index. Now we can decompose the total reward, the total expected reward from an episode when a policy pi, when an arbitrary policy pi is applied to the MDP as follows. So we can first condition on the initial state. So we can condition on the first state of the MDP that is chosen according to rho, okay, which is the initial state distribution of the environment or the MDP. Okay. And so if you want to think about a policy pi that maximizes this iterated expectation, any policy pi star that maximizes this, so it is sufficient for pi star to maximize the inner quantity over all possible realizations of the initial state. Okay. So let me just say here that so it is sufficient for a policy pi star to be to maximize let me define a new notation V1 pi of s. If we define V1 pi of s as the expected total return during an episode of a policy pi, given that the first state was a certain state small s and if we can somehow find a policy um, pi pi star for which no matter what the initial state s is, it always achieves the largest V1 pi of s over all other policies pi, then it follows that it will also maximize the weighted average of all these V1 pi of s's. So, because the reason for this is just because this object on top is just equal to the sum over all states, the probability that that state S is the initial state, followed by the total reward or the expected reward that the policy pi generates when started from that initial state. So, it is just a weighted average of these numbers V1 pi of S. So, if we can find a policy, a single policy pi star that uniformly maximizes V1 pi of S over all pi and simultaneously over all s uniformly across all initial states s, then it qualifies to be an optimal policy. Okay. So, by the way, the notation, the subscript notation 1 stands for the dependence on where we start summing the reward. So, here we are summing the rewards, individual rewards, all the way from round 1 to the final round capital H, and conditioning on the state at the beginning round, which is round 1. So, the 1 is essentially related to the one in the lower index in the sum, as well as uh, the time index where you condition on the state. Okay. So, let us start with this definition and try to expose some nice optimality properties of how pi star should look. So, let us start by beginning. So, in general, so since we now have a definition for V1 pi of s for any policy pi and any start state s at time 1, in general, let us define the reward to go function, or this is also called the value function of any policy pi at state s, starting from state s, and more importantly at round h within the total time horizon capital H as follows. So, we will just define this to be V subscript h pi at s, and the definition for this is the expected value that the policy pi would generate starting from stage h or time round h. So, let me say I equal to h to capital H. So, the start time or the starting round is in general small h instead of 1 Ri, given that the state at time h at time I at time h was equal to s. Okay, so this just generalizes the previous definition of V1 pi by allowing for an arbitrary time at which you start applying the policy pi. So, in this case it is the arbitrary round small h. Okay, so let us define Vh pi of s for any uh, h pi and s in this way, and we will also define notation. We will set up notation for the optimal value function. Be defined by. So, let us define Vh star of s for any state s as the largest possible expected reward starting from time h and going all the way up to time capital H of any policy pi starting from state s at time h, okay, for any h and for any state s. Okay, so this is more precisely the optimal value function from round h onwards. Okay, so that is Vh star of s, and so with this notation an optimal policy pi star is one that maximizes V1 star of s. So, it is sufficient for a policy to that maximizes V1 star of s for all states s, for all starting states s at time 1 to be an optimal policy for the entire MDP, okay, for the entire horizon, entire finite horizon. Also, one simplifying assumption that we will make, which is a very mild assumption, is that in the sequel we will assume deterministic rewards RSA, meaning that R of SA is actually a function that maps every state action pair into a real number representing the reward. Okay, so there is no loss of generality even if R of SA is a randomized function or a reward generated from a distribution depending on S and A. One can take an expectation over that internal randomness and redefine the reward so that there is a deterministic reward in expectation. Okay. So, this is just for simplicity, can be generalized. So, with this, here is a theorem, here is a result that characterizes the structure of an optimal policy for the finite horizon MDP problem, and this is often called finite horizon dynamic programming. So, the first part of this result states that for every state S and timestamp h within the time horizon, we have that Vh star of s, the optimal, the best possible value starting from state S at round h and going until the termination of the episode, is equal to the max over all actions of RSA plus, so the instantaneous reward plus a tail reward in some sense, which sums over all possible S prime T S A S prime into Vh plus 1 star of S prime. Okay, and specifically we denote so when small h is equal to capital H, we denote Vh plus 1 star of any S prime equal to 0 by convention or definition for all S prime. Okay, so the following relationship holds between the stage H optimal value functions and the stage H plus 1 optimal value function. Okay, so basically there is a instantaneous reward part and then there is a sort of a tail reward part. Okay, so the way to read this equation in words is that the optimal value that one can hope to start when you're starting at time h from state S is equal to the best possible action you could take at state S at time h, which we denote as A, that yields the best possible sum of instantaneous reward, which is R of SA. So, if you played action, if you decided to, if you contemplate taking action A at time h on state S, you would get RSA, instantaneous reward in your hand, followed by which you would transition with probability TSA S prime to a given target state S prime. And from then on, the best that you could probably have hoped to have done is to implement the optimal policy from stage H plus 1 onwards and collect an optimal tail reward VH plus 1 star of S prime. Okay, so in some sense this says that in order to be optimal at time H at state S, you essentially need to take the most rewarding action in the sense of total instantaneous reward plus tail optimal reward. And that's the relationship between the value functions, the optimal value functions of successive stages H and H plus 1. Okay. The second part of this result gives an explicit gives a way to find an optimal policy. So, in fact, it states that any policy pi, so by definition pi is a map that goes from S cross H bracket H to distribution over actions that satisfies for any state S, for any given state S uh, at any stage H, the support of the distribution of actions that it plays. So pi of S comma H is a distribution on actions that this policy would have played. The support of a probability distribution is just a set of all actions for which it has a positive probability of playing this action. So, if it turns out that for any start state S, for any intermediate state S at an intermediate time H, if the set of any action that it plays with positive probability belongs to, so is basically an action that maximizes RSA, the instantaneous plus the tail reward combination, into VH plus 1 star of S prime. Okay, so just to be clear, the argmax is in general a set. Okay, so all it says is that this policy ought to play any action that maximizes this sum. Okay, so for instance, if there are two actions that potentially maximize this sum, it can play either of these actions with arbitrary probabilities, but it must never play any action that is not the maximizer of the right hand side. Okay, so any such policy that satisfies this property for all intermediate states S and for all time rounds small h is an optimal policy for the MTP. So, in other words, V1 pi of S is equal to V1 star of S for all start states S. Okay, so this is essentially the nature of optimal policies, and the reason this is called dynamic programming is basically that you can use this successive relationship between VH star and VH plus 1 star and the second property to essentially find so you can firstly you can start from VH plus 1 star, which is defined to be 0. From this you can build up, you can compute V capital H star by applying this recursion. So V capital H star depends on V capital H plus 1 star, and going backwards in time VH minus 1 star depends on VH star and so on. So once you have computed VH for any small h, once you have computed VH star, you can basically go back in time and compute VH minus 1 star using property 1 and so on and so forth, and so you can eventually compute V1 star, and this is exactly what is called dynamic programming in the terminology of computer science algorithms, because once you have a value function at stage h, the optimal value function at stage h, you can compute basically in time polynomial in S and A the value function at time h minus 1, the optimal value function at time h minus 1, and that's all you need to go backwards in time, okay, to reach up to V1 star. So we won't go through the proof of this theorem in full detail, but let me probably mention the key proof idea here. So maybe let me sketch out the proof of property 1. The proof idea is basically to exploit the Markov property generated by the that arises Markov property of the trajectory arising from. So what is the trajectory? S1 A1 R1, S2 A2 R2 and so on, arising from the interaction of pi. So pi interacting with the MDP, a policy interacting with the MDP. Okay, so let me sketch this out. So in order to prove property 1, there are two parts to it. The first part is to show that there is an inequality here. Vh star of S is at most the right hand side, and the second part, which is the easier part in some sense, is to explicitly show that equality can be attained. Okay, so for the inequality part, what we will show, so the inequality part is the more interesting part of the proof, according to me. So we can start by writing Vh star of S. So for any, so consider any S and H. Okay. So recall that this was defined as the max over all policies pi of the um, the tail reward starting from time h at state S by the policy pi. So in turn, by definition, Vh pi of S is the expected value over pi in the MDP of the sum of tail rewards starting from h to capital H of R Si comma Ai, given that the state at time h was equal to S. This is by definition of Vh by S. Okay. Now one can split this sum in two parts. This sum one can split as I equal to H and then followed by the tail sum I equal to H plus 1 on all the way up to capital H. So if we do that, we just get the split sum. E pi. So the first term is when I is equal to H, plus the remaining part. So, we will just abbreviate R of SIAI as RI. Okay. Let us look at the first part here. So, given that the state at time h was equal to S, uh, what is the only random variable here that determines R SH AH? Well, it is precisely the AH random variable. So, AH is determined by the policy looking at state SH and deciding to play over a distribution of actions. And so, it is not hard to see that this is exactly equal to the sum over all candidate actions A, the probability with which the policy pi would have played the action A at time h, which in our notation is pi sh evaluated at A. So, this is precisely the probability that with which the policy pi executes action A at state S at time round h. Okay. And now we move on to analyzing the second term. So, let us do it here. The second term one can write as an iterated expectation. So, the conditioning here is only over SH equal to S, but we can condition also on the next state. So, let us do that. So, R of SIAI, we will bring back the R SIAI notation given SH equal to S, and let us also condition on whatever next state arises SH plus 1, followed by the outer conditioning over SH equal to S that remains, okay, by the law of iterated expectation. Now, if one looks at the inner expectation here, we have the random variable whose expectation is taken. This is a random variable that just depends on the trajectory from SH plus 1 onwards. So, it is SH plus 1, AH plus 1 and so on and so forth. So, that is what determines the total tail reward. However, the conditioning is on both SH plus 1 and SH. Okay. So, by the Markov property, we can basically drop this term. So, because it does not matter how you got to state SH plus 1, what you are going to evaluate is just the future reward, which does not have anything to do with states encountered before SH plus 1. So, you can drop this by using the Markov property. Okay. And now you notice that this conditional expectation conditioned on the precise state S h plus 1 is by definition upper bounded by the optimal value function starting from round h plus 1. Okay. So, internally the inner conditional expectation after dropping the SH equal to h term is no more by definition is no more than VH plus 1 star at SH plus 1, and then here is the outer conditioning on SH equal to S that stays as usual. Okay. So, this is just by the definition of VH plus 1 star at SH plus 1. Okay. So, the inner conditional expectation was for a particular policy pi, and it can be no more than the best possible, which is defined as VH plus 1 star at SH plus 1. And now the only thing that remains is to evaluate this conditional expectation under the policy pi. So, what is the setting here? We know that the state SH is equal to S, and we let the policy pi operate for one time instant. So, in response to SH equal to S, the policy pi would have taken a certain action H, which would have caused the MDP to transition to SH plus 1. So, this random variable whose conditional expectation is being taken is just a function of SH plus 1. So, all we have to do is to find the conditional distribution of SH plus 1 given SH equal to S under the policy pi, and that is simply the sum over all next states S prime, okay, of the probability under pi that the next state sh plus 1 is equal to S prime given sh equal to S into Vh plus 1 star of S prime. And this inner thing in turn, the inner probability p pi is in turn, by the definition of the policy, it's summing over all actions the probability with which the policy pi would have played this action at the state S at stage H into the followed by the probability that sorry, this is A, followed by the probability that the state of the environment would have actually gone from S to S prime under the play of the action A, and then finally you have Vh plus 1 star at S prime. Okay, so this is the explicit upper bound for the second term. And now if you look at both these, okay, I missed out a term here. There should also be in here an R of S comma A. Okay, so now if you look at adding these two, so this was the first term and this is the expression for the second term. So if you look at both these terms, then what you have is the summation over A being common and pi SHA being common, and then what you have remaining is RSA plus the sum over S prime of TSA S prime into VH plus 1 S prime. Okay, so this is at most the summation over all A of pi SHA, but we know that the sum over all actions A of pi SHA equal to 1. So you can upper bound the average by the maximum, and that is what gets you the max over all these. Okay, so that proves property 1, and property 2 is essentially property 2 essentially goes hand in hand with showing the equality part of the first part by explicitly exhibiting policies that only take the actions that maximize instantaneous plus tail rewards. Okay, starting from the last time horizon capital H all the way down to the first timestamp 1. Okay, so hopefully these details are enough for you to be able to construct a full proof of this result. Thank you.